It's a pleasure to introduce Dr. Laurence Perreault-Levasseur. So, Laurence is an associate professor at the Department of Physics at the University of Montreal. She has a joint position at the Quebec Artificial Intelligence Institute, also known as MILA. Laurence received a PhD degree in applied mathematics and theoretical physics at the University of Cambridge. She worked on applications of field theory methods to the formulas of inflation. Laurence is well known for research on cosmology and the development of machine learning techniques for data analysis and constraining cosmological parameters. And today she will talk about data-driven high-dimensional inference problems, a journey through strong gravitational lensing data analysis.
Thank you so much. Thank you so much for the invitation. It's really a pleasure to kick off this meeting. It's going to be a lot of fun. All right, so today I'm going to be talking about some recent work that we've been doing in my group at the intersection of inverse problems and high dimensions and astrophysics and machine learning. So if I was giving this talk a couple years ago, I would have probably started with a slide like this, saying that we live in a very special time in astrophysics because there's this brand new generation of sky surveys and new telescopes that are going to be taking insane amounts of data. It's going to be super amazing. But then we're about to be flooded by these massive volumes of data, and that's why we need machine learning. So this is not what I'm going to talk about today. This is true, but there's another thing about this data that's really important that I'm going to be talking about, which is the complexity of that data. Because with every new generation of instrument, the complexity of the data that we have is constantly increasing, so much so that our traditional analysis methods are just not able to keep up anymore. So what do I mean by this is that when we have simple data, simple parametric models with a handful of parameters are sufficient to capture the information that's available in the data. For example, and like for a lot of applications, we've managed to get away with that in astrophysics. So for example, if I have an image of a galaxy here that's really low signal to noise, I can fit a parametric model with two parameters to capture the surface brightness of this galaxy and manage to extract information in this data to get a pretty good fit. But the problem is that now if I have more complex data, like this is not going to work anymore, clearly. And so the question is, what do we do at this point? So the problem is that it's becoming more and more challenging to come up with analytic models that can capture the increasing complexity of our data. And so what I'm going to be talking about today is that one possible way forward is to learn this more complex parameterization through data with machine learning and specifically generative modeling. So this is my game plan for the talk. And in order to make things more concrete, I'm going to be using the specific example of strong gravitational lensing throughout my talk. Because I know that you guys are not experts in strong lensing, we're going to start by a short introduction to strong lensing. So strong lensing is the formation of multiple images of some distant object due to the deflection of its light rays by the gravity of some intervening structure. So let's say that here around the Earth, right here, and there's two galaxies, one right behind the other one. As the light rays of the background galaxy pass near the foreground galaxy, they get bent. And so they come to us from different angles. And as a result, here on the Earth, we can see multiple images of the same background galaxy. It's a little bit like looking at a fish through the corner of a fish tank. If you've ever noticed, you can see multiple images of the same fish. Okay, so here's Mr. Mango demonstrating this effect. So you can see that when he comes, he laughed. It took me so long to get this video. So when he comes to the corner, you can see two images of the same fish, and it makes images that are really similar to actual images of strong lenses that we see in the sky. So here, there's two images of the same background quasar because its light rays are bent by the gravity of the foreground galaxy in orange. Okay, so the only difference is that here light is bent because of gravity, whereas in the top light is bent because of refraction in the glass. So here's another example of a strong lens. So the background galaxy is the blue one, and it makes those arcs around the foreground galaxy in orange. And the reason for that is the geometry of the lens. And you can reproduce an effect like this at home really easily with a wine glass and a candle. So if you look at the flame of a candle through the foot of a wine glass, you can see that as they become aligned, the image of the flame of the candle wraps around the foot of the wine glass, and it makes images that are super similar to actual images of strong lenses. So here in this analogy, the flame of the candle is the background galaxy, this image is getting distorted, and the foot of the wine glass is the foreground galaxy that's causing the distortion. Okay, so in this like setup, what I meant before with simple data, we can get away with simple models, is that let's say I have simple data like this is here, which is a strong lens. I can parameterize the shape of the foot of the wine glass, and I can model it basically with like a handful of parameters. So, and specifically in the case of strong lensing, what this means is that I need to simultaneously infer the shape of like the foot of the wine glass and the undistorted image of the flame of the candle. So the foot of the wine glass, I can say parameterize it by just an elliptical blob of mass with just a handful of parameters, and the background source, like the flame of the candle, I can say it's a single Gaussian or Sirtix blob, for example. So just one blob for the background flame of candle and another blob for the lens galaxy. And if I do this very simple parameterization, the inverse problem I'm trying to solve has this form here, where Y is a vector that contains the pixels of the noisy lens image. L and S are the handful of number of parameters that describe the lens and the source, and they both non-linearly enter into the forward model F that maps those parameters into the states of where the data lives, like the lens image states, and then N is a vector of additive noise. Okay, so in this case, I can model those, I can fit those parameters to this data like this, and I get something like that. This is real data. You get a corner plot with few parameters because there's few of them, and this is real data, so I don't know what the truth is, but I can look at the residuals here, and they look pretty good. So there's a good chance I'm doing a good job. But then if I want to do a better comparison, what I can do is I can take this best fit model and then predict what higher resolution data would look like, propose to get that data, and then compare that data with what my model predicts. And this is what I get. And they agree pretty well. So there's a good chance that this is the correct model. So now the problem is when I have higher resolution data, so instead of looking like this, my strong lens looks like this. So I start to resolve more structure in the background source. This is not going to work anymore. My single image of one Gaussian blob for the background source is just not going to be sufficient. So I need a more complex parameterization for what the flame of the candle looks like. So what I can do is I can use a pixelated image for the flame of the candle. So if I do this, now my inverse problem looks like this, where now X is a vector that contains the pixels of the undistorted image of the flame of the candle. And now those parameters have become linear parameters. The lens parameters are still nonlinear parameters here, but they enter nonlinearly into a lensing matrix L. And when I multiply my vector of undistorted pixels by that lensing matrix, I get the lens image. And so this is really good. I managed to turn a nonlinear problem into a partially like linear inverse problem. So that should be really great. So let's try to on-lens this thing here to reconstruct the background source. For now, assuming that I know what the lensing matrix is, assuming I know what the shape of the foot of the wine glass is, let's see what I can do to reconstruct the flame of the candle. So this is the observation. This is what I'm trying to reconstruct. And the problem now is obviously not everything is rosy, is that if I have 100 by 100 pixels in my flame of candle image, this is like 10,000 free parameters I'm trying to reconstruct, right? And so because of that, my inverse problem is heavily under constraint. So to regularize it, I need to impose a prior on my background source pixels. And if this is pre-machine learning, the only thing I can do, because I need to keep things like tractable, is to use a Gaussian prior at some level, some version of a Gaussian prior. So if I do that, I end up with something like this as my best fit reconstruction. And obviously, this is not perfect. There's a lot of noise that leads to my reconstruction. And the reason why this is not great is because my prior is misspecified, because a 2-point correlation function is not a good representation of a galaxy. And so that's what's causing problems here. But let's say I don't care because my science is not in the background source. What I really care about is the foreground lens, because I'm interested in measuring the distribution of dark matter in the foot of the wine glass. That's what I want to do. So I'm still just going to use that and see if I can jointly infer the lens and the flame of the candle. So for a lot of the examples that I'm going to be using today, I'm going to be using background sources like flames of candles that are MNIST digits, because they make it really easy to see what's going on like intuitively. So here I know that this is a number, like the flame of the candle is a number, a handwritten number. And so I want to infer what that number is when it's not behind the foot of the wine glass and what the shape of the foot of the wine glass is. Like I want to do that jointly. And I know it's a number, so I'm going to go in the MNIST data set, measure the 2-point correlation function, and that's going to be my prior that I'm going to be using on my background source pixel. So if I do this, this is what I get. So this is my best fit number. It was a 2. And these are the parameters of the foot of the wine glass. So it looks pretty good. But if I look at this more closely, we see that clearly some of those parameters are biased. And so if we look at the residuals, they're good, but they're not perfect. And so to try to understand what's going on, we can look at the ground truth, which is this here. So we see that the source, that number 2 that we reconstruct, is smaller than the true one. And that's because our prior was 0-centered. So it's trying to make the background source as small as possible, to make as many pixels as possible close to 0. But the size of the background source is degenerate with some parameters of the foot of the wine glass, specifically the slope of the foot of the wine glass, and that's what's causing this bias, the correlation between the image of the flame of the candle and the foot of the wine glass. And so that's what's causing the bias here. And so what this means is that it's really important to be super careful about our choices of prior, even if we don't care about those parameters, because that's going to cause biases that are going to bias all of the science we want to be doing with strong lensing. So we're going to have to do something better. Specifically, it would be really nice. I've seen images of of galaxies that have not been lensed, and I know that what's behind my galaxy, my foot of wine glass, is a galaxy that's also like unlensed. So it would be really nice if I could learn my prior from examples of galaxies that I've already seen in the universe. So let's talk about data-driven priors. So the question is, can we learn to sample our prior from like data examples of images of galaxies? And it turns out that if we want to do that, the only thing that we need to do is to know what the score of the distribution is, which is the gradient of the log density of that distribution. So let's say that like an image of a galaxy is 1 point in a super high dimensional space. So here I'm just representing 2. So images of galaxies are going to fall on this manifold, like say those blobs here. And so if I wanted to learn to sample from that density, I could learn the density itself, which is going to be really hard because I'm going to have to know the normalization method. Like if I want to know the density at 1 point, I need to know where all the density is of the whole distribution because it has to be normalized. So that's hard. But if I just have to learn the score, now it's a vector field. So it only contains local information about my distribution. And that's much easier to learn. So I can train a neural network using star matching to learn this vector field, basically, at any point on this distribution. So I don't have time to go into the details of how that works. It's super cool. But once it's done, I have a neural network that I have trained to approximate this score function. And with that score function, now I can use Langevin sampling, denoising Langevin sampling to basically start from a realization of noise and then solve a reverse time stochastic differential equation to get a new example of a galaxy from my prior distribution. That's a different galaxy. That's just a fake galaxy. So I can generate a bunch of fake galaxies. Some of these are real galaxies, and some are not real galaxies, and I don't know which one's which, so I'm not going to ask you to guess. But if you want to make fake galaxies, you can go here. It's pretty entertaining. So now I can generate new galaxies. I can sample my prior. But that's not what I want. I don't want to make random galaxies that could be in the universe. What I want samples of the one galaxy that's sitting behind my lens. And so what I want is samples of my posterior, not samples of my prior. But if I want to sample my posterior, I need to score my posterior, which is this. Okay, I don't know that yet. But I do know Bayes' theorem. So I know that I can write this as the score of my likelihood plus the score of my prior. So my prior, I'm done. I know what this is because I approximated it with my score model. So now I'm left with the score of my likelihood. And because I've told you I already know my forward model, I know how lensing works. I know the physics. I can simulate it. That should be pretty easy. So this should be a done problem. But it turns out that it's actually really hard to approximate this because it's actually intractable. And so it's turned out that there's a huge field of machine learning now that are trying to come up with approximations for this convolved likelihood thing. And so there's a bunch of different approximations, different avenues that are possible depending on exactly which which field like which application you want. So some of them are like sort of guidance-based methods where you try to come up with an approximation for this specific integral to guide the diffusion of your prior into the posterior. You can just say, okay, I'm not going to try to separate this using base pair, but just going to try to approximate the score of the posterior directly with variational inference to generate like directly samples from the posterior. Some approaches are like variable things. So you do one prior diffusion step, one likelihood step, and you kind of iterate like that and you hope for the best. And sometimes those kind of can't converge to really good looking samples that are like basically prior samples that are kind of close to the posterior. So they're not like the best. And then there's sequential Monte Carlo where you generate a bunch of samples that are kind of approximately close to your posterior, use importance sampling to sort of iteratively converge towards where your posterior is. And the bad news is that in physical sciences, there's not one method to rule them all. They're all kind of like some of them work best on some problems versus others. And so that's unfortunate. But for our problem, because we know that our likelihood is Gaussian and our model is linear, and the likelihood is super informative, it's actually possible to write down a pretty good approximation for the convolved like integral. And so that's what we're going to be doing. We're going to be approximating the integral and use a guidance-based method to produce samples. And that's going to be actually a pretty good approximation. So let's see how well we can do. So let's say that this is my background source. So this is my flame of my candle. And if I forward model this, I'm going to get this lens model here. So I can make mock data with various levels of noise like this. So this is really like high signal to noise data. This is like very, very noisy data where I've destroyed all the signal, and see for all those mocks observation, what does my posterior look like? My posterior samples. So I can sample my posterior with this method. So in the case where I have really high signal to noise data, there's a lot of information in my likelihood. So there's going to be very small uncertainties in my posterior samples. I don't really need information from my prior, basically. So all my posterior samples are going to be very, very consistent with each other. There's going to be very little variability. As I increase the amount of noise in my likelihood, I'm going to destroy more information. So I'm going to need to pull some information from my prior. So that's going to increase my uncertainties between my different posterior samples. So the places where information has been destroyed, there's going to be more variability across the posterior samples. And because lensing, like in this specific configuration, it's mostly like the center of the background galaxy that's really magnified. There's more information about the center of the background galaxy, and the outskirts have been like sort of drowned as noise. So the outskirts are more variable across different posterior samples, and the central part of the background galaxy is more consistently reconstructed across the different samples. And then in the limit where I have just noise, no information in my likelihood, I just get random prior samples that are galaxies, just random galaxies, and nothing is consistently reconstructed across my posterior samples. All right, so this is pretty good. It's doing exactly what we think it should be doing. Sort of makes sense. Let's see if this is good. Also, if we're out of distribution. Let's say I have a galaxy that's very different from what I've seen before. So specifically, we looked at what if we had a galaxy that's in the shape of a 7? And I still want to analyze the data with the galaxy prior. What would happen? So I can make a bunch of different mocks with different levels of noise. So again, in the case where I have really high signal to noise, there's a lot of information in my likelihood. It didn't really matter that my prior is really misspecified. I'm going to get consistent 7s across my different samples because there's a lot of information in my data. But if I destroy information, I'm only going to get consistent, like significantly detect like the middle part of the 7 that's been hugely magnified, and the outskirts of the galaxy, well, the 7 are going to be interpolated with information coming from the prior, which is the galaxy prior. So it's going to smoothly interpolate between 7 and galaxy, which is the prior that I'm using. And then in the case where I've destroyed all the information in my data, I just get a random sample from my prior, which is a galaxy prior. And I'm not reconstructing consistently anything across my posterior samples. This is pretty good. But this is assuming that I knew what the shape of the foot of the wine glass was. In reality, I'm never going to know that. So let's see if now we solved our problem of small 2s that we had before when we were jointly inferring the foot of the wine glass and the frame of the candle. This is what we get. And we see that in blue is what I had before, and in green is using the score-based prior. That's been trained on M stitches. So we get that the 2 is the correct size. It's not too small anymore, and we have fixed our bias problem. So with score-based priors, we have managed to fix this inference problem. So this is a toy problem with like M digits as background source. In reality, we'd have galaxies, so you can show that for a more complex forward model and for a realistic background source, you also fix this bias problem using score-based priors. So this is great. Looks like we're in shape to apply this to real data and make a lot of fun discoveries. But there are problems. Specifically, the fact that I have assumed that my likelihood was Gaussian when I did my approximation from my convolved likelihood, and reality is not so nice. So this is noise. There's no signal in here. There's nothing. This is data from the Hubble Space Telescope and the James Webb Telescope, and this is just noise. There's no galaxies in there. There's cosmic rays. There's a lot of correlated noise. There's a lot of readout, like correlated noise of stripes and JWST, the 1/f noise. It's a mess, and it's clearly not Gaussian. This is not going to work. This is just too bad. If only I had a way of learning a more complex distribution from examples of noise, right? Oh, but turns out I can do this. I just need to look at examples of noise, and I can learn the distribution of my noise using score-based modeling. So I can train a score-based model to learn the distribution of the noise. And then I can sample new realizations of fake noise, which is this. So these are fake noises. The bottom row are fake noises. They look very similar to real examples of noise. And so now I can do two things. I can use this as a super realistic noise simulator and like do this in traditional like simulation-based inference to produce realistic simulations of my data. Or I can use this noise model, like this score-based model, as my likelihood to explicitly analyze, like explicitly sample data in explicit inference. So how does that work? Well, I have learned my score model approximates the score of the noise Q, but the score is with respect to my pixels in my detector. This Q, this noise model, that's exactly what my likelihood is, right? Because data minus model should be consistent with noise. And so when I'm doing Langevin sampling to sample my parameters, this is what I need to sample. So the score that I need to have here is with respect to the parameters that I want to sample. But what I learned is with respect to the pixels in my detector. So I can just use the chain rule and replace this, pull out the factor of Jacobian of my forward model. And because my forward model is auto-differentiable, I get that for free. And so I can sample using the same method, but with my data-driven likelihood. So this is an example of how this looks like. So I've injected a simulation of a strong lens here in a real patch of HST noise. And I've tried to do the inference assuming that noise was Gaussian using traditional methods. And I get the blue contours here, which are all very biased. And if I use this data-driven likelihood that I trained using real examples of HST noise, I get unbiased estimation. And this is just one example, but I can do that on a population of lenses and show that I get good coverage. So this is like accurate. Actually, I get accurate inference on using this method. So this is pretty cool. So this was we applied this to lensing data, but turns out that non-Gaussian noise is a problem that many people have. So we've applied it also to loud glitches in gravitational wave detector at LIGO. Because glitches are super non-Gaussian, they're very loud, they're really hard to model. So instead of like modeling them and subtracting them from the data, we can just marginalize over them using a data-driven likelihood. We've used this to do transit spectroscopy with James Webb to try to extract more accuracy spectra because 1/f noise is really hard to model and to subtract from data. We also use it for with HST for PSF deconvolution and denoising to get galaxy images that are very similar in resolution to what you would get with JWST without ever knowing that JWST existed. And we also applied it to protoplanetary disks imaged with ALMA, well, measured with ALMA, with interferometry to reconstruct the images. So these are just some examples of the things that we can do with this. All right, so now looks like we're good to go to sample real data. But then, okay, so I've showed you that I can produce like nice looking samples that make sense, but how do I know that they're the samples that I actually, like they're real actual posterior samples? So this is the question of accuracy. How do I know that the samples that I get are really accurate? And this is especially important in astrophysics because really often we care about those posteriors because we want to marginalize over them. So we really care not just about sampling the peak, but also the tails because we want to integrate everything to get like hyperparameters. And so it's really, really important for this case. So basically we need to like answer two questions to measure like accuracy. We need to answer the fact like if I have this like inference pipeline that allows me to sample potentially in really high dimensions, how do I know that this pipeline is accurate, like that it produces samples of my posterior? And then second, if I have a component of that pipeline that's a generative model, like let's say a score model, how do I know that this is representing the distribution I think it's representing? like, how do I know that it's producing samples from the same distribution as my like data generating process that like actually produce my training data or my test data? So let's go into that. So first question. So typically, if I have like some collection of like lens images or like data that I want to analyze, accuracy of an inference pipeline is measured with coverage tests. And so the expected coverage probability of like a credible region is basically over that whole ensemble is the fraction of time that my ground truth is going to fall inside that interval. And usually you'd like that fraction to be equal to the mass of probability inside that like region. And so if you have an accurate estimator for your posterior, for every value of like the posterior mass, you'd like the fraction be equal to that mass. So you'd get like a diagonal plot if you plot like credibility, well, like posterior volume versus like expected coverage. And if it's not accurate, it's going to be non-diagonal. So typically this is assessed using the region that has the smallest support for a given volume. So that's the highest posterior density region. But there's a lot of problem with doing that, specifically in high dimensions, like over image space. The first thing is that it's really hard to know where's the highest density region when I'm in like 500,000 dimensions. So it's going to be really noisy to try to estimate that. So that's the first problem. But then the second problem, which is maybe even more important, is that it's a necessary but not a sufficient condition for calibration. So for example, let's say that I have a symmetric posterior like this, and I know, and like my ground truth happens to always fall on the right side of the peak of my posterior. I can have perfect calibration if I just look at the highest density region, but I know that it's biased because I know for a fact that I'm giving some probability volume over a region where I know that the ground truth will never fall. And so this is a biased estimator, but I would have a perfect coverage plot with the traditional way of doing this. So with Pablo and Adam, what we did is that we designed a new way of coming up with those regions, like with random points. And so by cutting those regions randomly, now we can define the coverage by just looking at distances between points, which scales really well to high dimensions. And we've also proved that doing it like this is a sufficient and necessary condition for calibration. So we know that if we pass the coverage test, like if we get a diagonal line, we're guaranteed that we're calibrated. It's fit installable, it's super simple. You should check it out. So it does like what we think it should do. In the case where it's calibrated, we get the diagonal line. In the case where we're not calibrated, we get a not diagonal thing. But more importantly, in the case where it's biased, where the highest posterior density region would make you think that you're calibrated, you can detect that you're not calibrated. Okay, so this is great. The only thing that I'm going to come back to is like, it's not really clear how to interpret a non-diagonal line. So that's like not so good. It's also not clear, like if you're not exactly on the diagonal, how close is close enough, it's not quite clear how to know that. So yeah, these are things I'm going to come back to in just one moment. I'm doing with time. You can stop me whenever you're done listening to me, but you can keep on talking forever. Okay. So, all right. So this is like, so now we have a test that works in high dimensions where we can assess the accuracy of our posterior samples. So this is really good. And now second question was, if I have some like components that's a generative model in my inference pipeline, how do I know that I'm capturing the distribution that I want to be like modeling? Okay, can I quantify this accuracy? So this is PQ Maths, another paper that was published last year. So basically, this boils down to the question of like, if I have two sets of samples, one set could come from my generative model, one set could be my training or my test set that comes from like my real data generative process. I want to know like what's the probability that they come from the same underlying distribution, right? So if I knew what that density is, I could say, okay, in this, and I cut one region, I could say, okay, like the probability of getting like two red samples out of like this region, and this region versus like the whole number of samples that I drew is going to follow a binomial distribution. And similarly for the blue samples, right? If I knew like what the density was inside that region. And then if I have if I tessellate the whole space instead of just looking at one region, it's going to follow a multinomial distribution. Okay, so if I assume the null hypothesis, that like under the null hypothesis that they both come from the same underlying distribution, I can define multinomial distribution. I can define statistics like this, and then we can show that this statistics under the null distribution is going to follow a chi-square distribution. So basically, it's going to follow Casper distribution with the number of regions minus 1 degrees of freedom. So that works if I have a synthetic distribution, like a bunch of Gaussians, like 20 Gaussians in 100 dimensions. It's also going to work for natural images like m digits. So if I repeatedly deselect my space and I calculate the statistics over every tessellation, my statistics is going to follow a Casper distribution. So this is super powerful for 2 reasons. First of all, it works directly in pixel space. I don't have to compress my data with any compressor. And so if my compressor was blind to some feature of my data that I might be interested in, like the noise, for example, which usually compressors are, then I'm going to be working directly in pixel space. I'm going to be able to be sensitive to things like that. Another thing is that because I only need to be able to know in which region my samples fall, I only have to be able to calculate distances in my space, which scales really well to high dimensions. So we've tested it in 500,000 dimension, but now I think we've tested it in 2 million dimension, and it still scales really well. So this is 2 really powerful things for this, and I only need to be able to define a distance metric to be able to use this stuff. So one fun application we can do is we can use it to compare the accuracy of a bunch of different generative models, even if they don't have the same architecture. So let's say I'm trying to train a generative model on this. Initially, I have 2 diffusion model and 2 VAEs. Initially, they're all equally bad, so they're very far from the optimal peak of the Casper distribution. But then as I train them, they get closer and closer with the samples that they generate. And then the VAs are not as good generative models. They kind of plateau pretty high, pretty far, because the samples they generate are not in distribution. And then the diffusion model they converge closer. Okay, so we didn't try to work very hard to make them really good, but it's just to show that you could get better, but it's to show that you can basically objectively compare different generative models to see how well they're representing the distribution you're trying to model, which is a useful tool if you're trying to use those models as priors, for example. Another fun applications that we looked at was if we have emulators, if we have very extensive simulations and we want to train an emulator, we can compare the accuracy of different emulators to see if they can generate the whole spread of simulations that the expensive simulator can generate. We can also use this to compare different simulation codes. So for example, in cosmology, there's a lot of different ways to integrate n-body simulations with adaptive meshes, and we can use this to compare different integration choices, basically. And we can show that even at the field level, we can detect differences between different codes. So this is very powerful to detect differences between codes or emulators. All right, so so I've mostly used examples that come from astrophysics and image data or volumes, but you can also use it for whatever modality you like, as long as you can define the distance metric on that modality. So we've also shown that it works for protein sequences and tabular data, and so things like catalogs and stuff like that. And so this is a very powerful tool. So it's also pivot solvable. So you should check it out as well. Okay, so this is really good. But it only works on marginal distributions. And so I mentioned before that when I had my accuracy test, my TARP test, with the diagonal line, it was not super good that if I didn't pass the TARP test, I didn't know how bad it was. And it was also really hard to rank models, because if they're one model gives me an S and the other one gives me an S in the other direction, or just under the diagonal, it's not clear how I compare models. So it's really good to have something that's more a score, PQ mass, but that also works on conditional distributions. And so that's another paper that was just accepted at ICML last week, 2 weeks ago. Anyway, spotlight paper ICML. And so this is Mira. So we basically have adapted the PQ mass score, but to make it work on conditional distribution. So now we can quantify the accuracy of conditional distribution. And instead of taking a more frequentist approach, we've taken more a Bayesian approach on assigning a probability to different models. So that allows us to rank different models in a way that's sort of systematic. And we've shown that in expectation, this score converges to a fixed value. So it doesn't matter how many samples we have or how many times we redo the tessellation, we're going to converge to some specific value for different models. So we can actually rank them in a way that doesn't depend on the choice of how many the stereo samples I have, for example. So that allows us to do things like ranking different, so we can detect if the forward model is misspecified, if the likelihood noise model is not good enough, if the prior is misspecified and things like that, and we can rank how much it affects the accuracy of a posterior across different models. And we have also applied it to other things that are not strong lensing, like black hole imaging, with like that tend to use these plug and play prior methods. And what we realized, we were very surprised, is that a lot of those plug and play prior methods that people use give very nice looking samples, but they're extremely overconfident. So they produce very biased posteriors that are very not accurate because their uncertainties are not broad enough. And so that was an interesting thing we realized with this. Right. Am I doing time? This is wonderful. Maybe I'm talking too fast. I should just slow down. Okay, sorry. I tend to speak too fast. I'm sorry. Okay, so let's talk about out of distribution accuracy. It's like I spent like probably the first half of my talk trying to convince you that it's really important to have a prior that is in distribution. Otherwise, we're going to be really in trouble. And then I tell you, we need to go take galaxies that we've observed in local universe and use that as prior for the flame of candle that's like behind my lenses. These are very different populations of galaxies, and galaxies have this tendency of like evolving throughout the evolution of the universe. So very distant galaxies, they look very different. Their morphologies are very different than local galaxies. And then I'm saying that like we should use that to train our prior. And clearly that's going to be a misspecified prior. And then say, okay, that's not what I'm going to do. I'm going to go to simulations and use simulations of high risk of galaxies as my prior, like to train my prior. But that's also going to be misspecified because we know that simulations are not perfect. So should I worry about this? On the answer is like, yeah, I should probably worry a lot. But then the thing is that we're going to be in a situation where soon with like L-associated nuclide, where like we already have like 1 or 2 orders of magnitude more strong lenses than we used to have, and we're going to have 10 to the 5, like hundreds of thousands of strong lenses. And so at a population, if we start doing inference over like the images of like the background sources, and we see that with something like PQ mass, the distribution that we get for the images of background planes of candle is very different than what we started with as our prior. We know that our prior is misspecified. So we can detect it. Like we definitely can detect the fact that there's a problem in our prior with this. So basically the question is, could we actually frame this as a hierarchical inference problem and learn this population level prior of galaxies hierarchically? With like an initial guess and just update our knowledge, I would see more and more observations. So the problem we'd like to solve is something like this, where like now thetas, the hyperparameters of our inference framework, are the parameters of our diffusion model. These are the things that we'd like to do inference over because they describe the population level distribution of galaxies. So that's in theory what we would like to do, ideally. But this is really complicated because then I'm going to get the distribution over my diffusion model parameters. So I'm going to get an ensemble of diffusion models as my prior. So that's going to be like way too hard. So I'm not going to do that right now. But instead, what I'm going to do is I'm going to go empirical base about this and do this instead, where I'm just going to pick the diffusion model that maximizes the likelihood of my data in this like hierarchical framework. And so I'm going to do that. And then I'm going to do that iteratively, basically, with like expectation maximization, basically, where like I'm going to do a first round of inference over a bunch of lenses, get a bunch of posterior samples, and over 4 different lenses. That's going to be my first approximation. I'm going to create a new prior model, do another bunch of inference on a new population of lenses, and then keep on going like that until it converges. So, let's see. Okay, lots of math for something that actually I can just show you. It's going to be easier. So what does it look like in practice? So let's say that like the real galaxies that are behind strong lenses, they look like this. So they're blue spiral galaxies. This is not real, like this is just like a made up example. But let's say that they're blue spiral galaxies. But I've never seen on lens blue spiral galaxies. The only thing that I've seen are local galaxies that, for example, look like red elliptical galaxies. So the question is, can I discover that blue spiral galaxies exist just by looking at their length dispersion, starting from a distribution of these things? Okay, because I would train my initial prior on this because that's the only thing I know, but then can I discover that these spiral things exist? Okay, and this like actually really matters because the only thing I'm going to be looking at are lens version of these spiral blue galaxies. And so from this noisy observation, I would like to discover that the ground source is this, that's sitting behind. But with my initial misspecified prior, the best thing that I would be able to get is like something like this. Okay, so it's going to be like very different. Whereas if I had the correct prior to do the same analysis, I would have gotten this. okay, which is much closer. And the only difference here between those two examples are that this one has the wrong prior using my local like red galaxies, and the other one has the actual correct prior that's in distribution. So it's very important to be able to like update those priors. Okay, so go back to MNIST to make it more concrete if galaxies are not your cup of tea. So let's say the real universe has all the MNIST digits as background sources, but I've never seen 4s at all. So I don't know that 4 exists. The question is, can I discover that 4 exists? So initially, I'm going to train a diffusion model on all those numbers but 4, because I've never seen that 4 exist. So I don't know that's the thing. And I'm going to try to discover if there's something I'm missing in the universe. But I'm only going to be looking basically at, like, let's say there's a 4 that's behind my lens, and it's going to be lens, and then it's going to be noisy. So using only those observations, I'm going to try to discover that my prior has a problem and learn what that problem is. Okay, so initially, if I do this inference with my misspecified prior that doesn't know that 4 is a thing, I'm going to get a 9. Because 9 is kind of like 4. But it's going to be a bit of a weird 9. Like it's going to be a bit more square than typical 9s. So then I'm going to do a bunch of those inferences, and I'm going to train a new prior on those kind of like all the digits plus a little bit weird 9. That's kind of an extra mode that's starting to develop. And if I do that, like initially I get those a bit weirder 9. And then after another round, I get something that's even more square for those 4s. And then it starts to separate. And then the mode of 4s kind of starts building with the iterations. And then eventually I managed to discover that there's a new number that I did not know existed just by having looked at like lens digits. I never saw a 4 that was not lens in the sky. I've just updated my prior in a hierarchical way, and I've discovered that this new thing exists. So this is like the example on 4s. Now, if we go back to the galaxy example, so if we start from so these are the transits at the bottom we're trying to reconstruct, and we look at those observations at the first round, this is what we're going to get. The colors are a bit better, but they're still very red, and definitely we don't have any structure in the galaxies. But they're different than in distribution galaxies because their color is different and their shapes are a bit different. And so after 10 iterations of this, like training a new prior, we managed to discover that they have the correct color, and we managed to see like much more complex structure in the galaxies. So we've discovered that spiral blue galaxies are a thing just by looking at lens version and adapting our prior and with this process. Okay, so I'm going to skip. So we can actually do the same thing. This was the prior that was misspecified. But another problem that's really common in machine learning is like misspecified forward model. And so you can actually extend the same framework to tackle misspecified forward models. But I'm going to skip that because what I really want to show you is data. Okay, so we can put all of this together and apply it to real data to see how well we can do. So I'm going to start with this example, which is a lens that was discovered in 2006. And it was imaged with the Hubble Space Telescope in I think it was 2008. And so the first lens model that was published for the background source image looked like something like this in 2008. And then it's been reanalyzed a couple times since. And the background, so these are the reconstructions of the flame of the candle. They don't really look like galaxies. But then when we applied our framework to this data, we get this here. That looks a lot more like an actual galaxy. And we can start to think, okay, we can study things about these things. And not only do we get the best fit like sample, but we also get the whole posterior, so we can get samples of these galaxies, and we can start quantifying the certainty with which we reconstruct certain features. Like, for example, it's definitely a spiral galaxy, because even if the shape changes, those like morphological features are consistently reconstructed across the different posterior samples. And things like star forming like regions and blobs, they're also consistently reconstructed, and we can quantify the uncertainty over their shape and their sizes. So we can start studying physics about those background galaxies at high redshift. So that's pretty cool. We can look at how well we're doing at modeling the data with these models. Like, what do the residuals look like? So these are our residuals. So this is the data that you look at the top. These are the models, and the middle are the residuals. And we can compare that with the residuals that previously published papers had. So the best model for this galaxy, these are the residuals that they had. So we can manage to fit the data a lot better than what was possible before as well. So not only that, but we can also use it as scale to model a bunch of different lenses. So this is a whole population of background sources that we have like reconstructed from modeling different lenses. And like, it's probably too small for you to see the scale of these things, But like the top one, the bright blob that's in the middle, is about 100 to 150 parsecs, and it's at redshift about 1, and it's a star-forming region. And so it's really amazing to be able to resolve consistently like those such small scale features in like really early galaxies that are like very far in the universe. And so just to give you an idea of like how amazing it is to resolve all those details, this is what those galaxies would have looked like if they had not been behind the lens to be magnified. So like the magnification of this strong lens really allows us to resolve a lot more features in the background versus to do like study of galaxy formation. So so that's all I have. I'm going to stop here with final thoughts about the fact that, I've given like a lot of examples about strong lenses, but I think a lot of the challenges that I talked about are common to a lot of different inverse problems in astrophysics and in other sciences. And I think that by tackling the problem of the high dimensional inverse problem, that really allows us to open the black box by looking at where is the information coming from in our inference, investigating like in the posterior samples, like what are the features when we get information, where is it coming from in the data, and sort of really start to build some trust into using machine learning model for science. So thank you.